Everyone. So my research component is multimodal emotion recognition and image generation system for mental health monitoring and emotion awareness. Channel Katsanarapna and my student ID is W19337 and IIT ID is 2022-0107. So this is the agenda overview of the today's presentation. When it comes to the problem statement, there are some main points that I need to identify. So the first one is mental health crisis. Increasing prevalence of mental health issues globally, highlighting the need for the early detection and intervention. Second point is lack of early detection tools. These existing methods for identifying mental health problems are all subjective, time-consuming, and reliant on self-reporting. Third point is inadequate monitoring. Continuous monitoring of emotional state is challenging, limiting the ability to provide timely support and intervention. Last point, technological gap. It is for the limited integration of advanced technologies like facial recognition and emotion detection in mental health diagnostics. When it comes to the research gap, there are mainly 3 points that I need to discuss. The first point is limited use of multimodal data. Existing studies predominantly use single model data, either facial or textual data for emotion detection, lacking comprehensive multimodal approaches that integrate audio, text, and visual data for improved accuracy. The second point is real-time emotion detection. There is a subsystem capable of real-time emotion detection and analysis, which is crucial for timely intervention in mental health issues. Third point is diversity of the datasets. So the current emotion detection systems often rely on the datasets that do not represent a wide range of demographic and cultural diversity, potentially leading to biased outcomes. The main points of the project aims are develop comprehensive emotion detection system, ensure real-time monitoring, improve user engagement, and contribute to academic and practical knowledge. When it comes to the design of the system, this is the architecture diagram of the design system. So there are 3 main tiers: data tier, logic tier, and the presentation tier. On the data tier, I have 2 layers. The first one is temporary database for perceived emotions. This is the layer that stores and manages the system's data. It provides centralized repository for storing user information, system settings, and other relevant data. In the context of an emotion recognition system, the data tier might include a temporary database for storing emotional data that is being processed. The second layer on the data tier is save the trained model. This component refers to the process of saving the trained emotion recognition model for later use. This is an important step in the model development process as it allows the model to be reused and shared with others. The second tier is logic tier. Under logic tier, I have 3 components: CNN model, emotion recognition algorithm, and NLP algorithm. CNN model. A convolutional neural network is a type of deep learning model that is commonly used for image and video recognition tasks. In the context of an emotion recognition system, the CNN model is used to analyze facial expression and identify emotional cues. Emotion recognition algorithm. This is the algorithm that is responsible for recognizing emotion based on the user's input. It might include techniques such as facial expression analysis, speech pattern recognition, or natural language processing. The third component under logic tier is NLP algorithm. NLP, or natural language processing, is a field of studies that focuses on enabling computers to understand and interpret human language In the context of an emotion recognition system, NLP algorithm is used to analyze text inputs and identify emotional cues. The third tier is presentation tier. Under that, we have three layers: capture emotions, generate emotion, and feedback. Capture emotions. This component refers to the process of capturing emotional data from the user. This might include capture facial expression, analysis of speech patterns, or processing natural language inputs. Generate emotions. This component refers to the process of generating emotional responses based on the user's input. When it comes to implementation, this is the technology stacks that I have been used. So I talk the summary of the technologies. As the programming languages, I have used Python and JavaScript. As the development frameworks, the tools are TensorFlow, Flask, and React. Libraries are NumPy, Pandas, Matplotlib, Scikit-learn, Pillow. And IDE is Jupyter Notebook and VS Code. As the version control, I have JIT and JIT. First, let's go through the concept or language that I use for the face emotion recognition. So in the first cell, I have imported the native libraries to connect with the model, and then in the second cell, this cards input checks for the availability of a CUDA-compatible GPU and sets the device variable to either the GPU or the CPU accordingly. Here it will print an appropriate message to inform the user. This ensures that the machine learning model training can leverage GPU acceleration if available, otherwise it falls back to using to the CPU. The next line sets the path to the directories containing training and testing images of the project. So the train underscore dir, this line defines a variable train dir and assign the string images/train, which represent the paths to the directory where training images are stored. In the second line, test underscore dir. Similarly, this line refers to a variable test directory and assign it in the string images test directory, which represent the paths to the directory where the testing images are stored. Function create data frame is designed to traverse a directory structure and collect the file paths and labels of images stored in the subdirectories. The OS module provides a way of using operating system dependent functionality like reading or writing to the file system. The function takes a single argument dir, which is expected to be a path to the root directory containing the subdirectories of images. This list will store the full paths to all the images found. Labels a list. This list will store the labels corresponding to each image. The label is typically the name of the subdirectory containing the image, which often represent the class of the image in the classification task. Then we have for loop. This loop iterates over each item in the directory specified by the dir. It assumes that each item is a subdirectory representing a label or class. Then the next loop iterates over each file in the subdirectory corresponding to the current label. Line constructs the full path to the image file and appends it to the image path list. After that, it appends the current label to the current label list. And finally, it prints a message indicating that all images in the current label or the subdirectory have been processed. Then it will return the list of the images, paths, and the corresponding labels. This code snippet creates a Pandas data frame to organize the image path and their corresponding labels for further processing and analysis. These lines create an empty pandas data frame called train. This line calls the create data frame function with train dir as the argument. The function retains true lists, image path, and the labels are then assigned to two columns in the data frame. Image. This column will contain the file paths of the image, and then we have the second column, train labels. This column will contain the labels for the categories of the image. It is similar to the one of the training data that applies to the test data instead. It creates the pandas data frame to organize the image paths and their corresponding labels for the test data set. This line creates an empty pandas data frame called test. The line calls the create data frame function with the test dir as the argument. The function returns two lists. One is image paths and the second one is the labels. These lists are then assigned to two columns in the data frame. Test image column will contain the file paths of the test images, and test labels column will contain the labels of the categories of the test image. This function, extract features, is designed to extract the features from a list of images. It assumes that the images are grayscale and it converts them into an NumPy array before reshaping them into a format suitable for further processing, likely for use in the machine learning model. Extract features takes the list of image paths as an input. This loop iterates over each image path in the images list. For each image, it loads the image using load_ing, setting the grayscale equal to true to load the image in the grayscale mode. The loaded image is then converted into a NumPy array using np.array. The NumPy array representing the image is appended to the features list. After all images have been processed, the features list containing NumPy array representing each image is converted into a single NumPy array. The shape of the features array is adjusted to have dimensions, number of images, height, width, and channels, assuming each image has the size of 48 into 48 pixels and is grayscale. The channel dimension is set to 1. The function returns the extract feature as the NumPy array. Image part assumes that the train is a data frame with a column named image which contains path to the training images. Then a features train image is calls the extract features function with the list of image paths training image as input. The extract features function will iterate over each image path, load the corresponding image, convert it to an NumPy array, and append it to the features list. Finally, it will convert the features list into an NumPy array and reshape it to the appropriate dimensions. The resulting training features will be NumPy array containing the features extracted from the training images. This assumes that the test is a data frame containing a column named image with words path to the image, test images. After that, extract features text image calls the extract feature function with the list of image paths test image as input. Inside the extract features function, each image path is iterated over each image. It loads the image, convert it to an NumPy array, and appends it to the features list. After processing all images, the features list is converted into a NumPy array and reshaped to the appropriate dimensions. The resulting test features will be an array containing the features extracted from the test images. Train and X_test are created by normalizing the pixel values of the training and testing image features respectively. Train features and test features are arrays containing the extract features from the training and testing images respectively. Each pixel values in these arrays represents the intensity of the corresponding pixel in the original image. By dividing each element of train features and test features by 255.0, getting the pixel values to be in the range 0 to 1. This is done because the pixel value in the typical grayscale or RGB images are integers in the range of 0 to 255. Dividing by 255 ensures that the pixel values are normalized to the range of 0 to 1, which can help improve the convergence and stability of the training algorithms. The resulting X_train and X_test arrays containing the normalized pixel values of the training and testing images respectively and are suitable for the training machine learning models. In this course, we are using scikit-learn's label encoder to encode the labels from the label column of the training data. sklearn preprocessing import label encoder. This imports the label encoder class from scikit-learn's preprocessing model. The label encoder is used to encode the categorical labels with the integer values. The label encoder instance layer is used to transform the categorical labels from the label column of both the training and the testing datasets into encoded integer values. Function to categorical calculus is used to convert the encoded integer labels into one-hot encoded vectors. To categorically _train, noun classes equals 7. This line converts the encoded integer labels y_train into one-hot encoded vectors. The toCategorical function calculus is used for this purpose. It takes the encoded integer labels y_train and the total number of classes as arguments and returns the corresponding one-hot encoded vectors. Categorically, y_test noun_classes equals 7. This line similarly converts the encoded integer labels y_test into one-hot encoded vectors using the same approach. After these transformations, the y_train and y_test will contain one-hot encoded representations of the categorical labels, where each row corresponds to a sample and each column corresponds to a class with a value of 1 indicating the presence of that class and 0 otherwise. Defines the convolutional neural network or the CNN model using the Keras sequential API. This initializes a sequential model which is a linear stack of layers. These are the convolutional layers followed by the max pooling and the dropout layer. Each convolutional 2D layer applies a 2D convolutional operation on the input data. The first argument specifies the number of filters and the kernel size parameter defines the size of the convolutional window. The activation parameter sets the activation function for the layer, and in this case its relevant. Pooling 2D layers perform max pooling operation to reduce the spatial dimension of the input volume. The pool size parameter defines the size of the pooling window. Dropout layer applies dropout regularization to prevent overfitting by randomly setting the fraction of input to 0 at each update during the training. The parameter 0.4 sets the dropout rate to 40%. The plugin layer converts the 2D output of the convolutional layers into 1D array to feed into the fully connected layers. These layers are fully connected layers. The first length layer has 512 unit with ReLU activation, followed by a dropout layer with a dropout rate of 40%. The second dense layer has 256 units with ReLU activation, followed by a dropout layer with a dropout rate of 30%. The output layer consists of 7 units with softmax activation. Softmax activation is commonly used for multi-class classification problem, as it converts the outputs into the probability values indicating the likelihood of each class. It is configured to use the Adam optimizer, categorical cross entropy loss, and accuracy as the evaluation metrics during training and testing. So these are the standard choices for many classification tasks, especially when we are working with the deep learning models. Method is used to train the model on your training data. These arguments specify the input features, extreme, and the target labels while trained for training models. Extreme contains the input features, train contains the corresponding one-hot encoded labels. Batch size is 128. This specifies the number of samples per gradient update. In each training iteration, the model will process 128 samples before updating the model's parameters. Adjusting the batch size can affect the training speed and memory usage. Epochs are equal to 100. This specifies the number of epochs or iterations over the entire training dataset to train the model. The model will be trained for 100 epochs, which means it will see the entire training dataset 100 times during the training. This specifies the validation data to evaluate the model's performance after each epoch. X_test contains the input features of the test dataset, and Y_test contains the corresponding one-hot encoded labels. During training, the model will not use this data for updating its parameters, but will evaluate the loss and matrix on it to monitor performance and defect overfitting. With these settings, the model will be trained on the training data for 100 epochs using batches of 128 samples per batch. Each epoch, the model's performance will be evaluated on the validation data. The training process will aim to minimize the categorical cross-entropy loss on the training data while maximizing the accuracy. We save the train model architecture to a JSON file and saves the train model weights to an HDF5 file. After that, the code snippet loads the pre-trained model from the JSON and HDF5 files. The audio emotion recognition model. First, I import the required libraries like this. After that, to load an audio file in Python using the librosa library, we can use the librosa.load function. So this code will load the specified audio file and print the sample rate and the first 10 samples of the audio data. And then using the matplotlib library, I generate the graph like this. This code section is performing the short time Fourier transform models STFT on an audio signal to create the spectrum, and then it is going to display the figure like this using the matplotlib. I set labels according to the and the gender like this. After that, using the pandas library, I add those labels or the healing list into a data frame. Then getting the features of the audio files using the librosa. This provided code is processors a list of audio files and extracts their NFCCOFs, null frequency threshold coefficients values, features using the LibRosa library and stores these features in the pandas data frame. I initialize an empty data frame with a single column named feature. It sets a counter bookmark to keep track of the data frame or index. Iterates over the list of my list containing an audio file names, then filters out the certain files based on conditions applied to parts of the file names. After that, loads the audio file from the raw data directory using librosa.load with the specified parameters. The rest type CursorFast is used to acting as a resampling algorithm, and then the duration is set to 2.5 and the load is 2.5 seconds of the audio. SR value is the target sampling rate and the offset equals to 0.05 is used for the start reading the audio after the first 0.5 seconds. Onwards the sample reads to an archive array. After that computes the MFCC features and takes the mean of these features across time. Here I created a new data frame called new FD. After that, to divide the dataset into train and test, I used the Boolean array new FD1, where the approximately 80% of the values are true and 20% are false. The data frame contains the rows where the new FD1 is true, and the test data frame contains the rows where the new DF1 is false. This print rows 250 to 259 of the trained data frame. In this part, I'm going to prepare the training and testing data for a neural network by converting the features and labels into the appropriate formats and encoding the labels. This converts the features and the label lists into NumPy arrays. The label encoder is used to convert the categorical labels into numerical labels. So in here, .fit transform is used to fix the label encoder on Y-train and transform the labels into integer. And then np-utils to categorical is used to convert the integer labels into one hot encoded format, which is suitable for neural network output. Sequence for the CNN model. np.expand_deans is the function that is used to add an additional dimension to the array at the specified axis. For the audio data processed with the CNNs, the typical shape is first dimension represents the single channel that is similar to the grayscale images having a single channel. So this code takes the features of the data, encodes labels, and prepares the feature data for input into the CNN by adding the required channel dimensions. Now I build up the CNN or the convolutional neural network using the Keras library, specifically designed for 1D data such as audio signals. So when talking about this module architecture, here I use kernel 1D layers, that is for the several 1D convolutional layers with ReLU activation and the same padding to preserve the input shape. After that, as the activation layers, I use ReLU activation function after each convolutional layer. Then dropout layers. Dropout layers is used to prevent the overfitting. Then pooling layers to the As the pooling layers I have used mask pooling 1D, it is to reduce the dimensionally and extract the dominant features. Then flatten is used as the 3D output to 2D layer. Then dense layer is the fully connected layer with 10 units. After that, I used activation as softmax activation for the final dense layer to the output probabilities. Summary is generated like this, and then to get the accuracy value, I compile the model and then fit the model with the batch size of 32 and the apertures of 1009. In the accuracy and the last graph, here also I use this method, the sigmoid method, to plot the accuracy and the log graphs. Then to save the model, I use this method and save the model as h5 file as emotion was detection model.h5. Then I predict the data according to this method using model.predict method with the batch size of 32 and verbose value as 1. So these are the prediction values that I got, and then I compared the predicted values with the actual values like this. In here, to detect the audio emotion recognitions, here I need to upload a WAV file. So this is the WAV file that I have choose to upload.
This coffee sucks!
So let's see the emotion. So here first you need to click on this choose file button, and then from there click on that file, and then it will be displayed in here, the WAV file. After that you have to click on the upload button. Then it will generate the emotion with the relevant emoji and the relevant. After the testing and evaluation, this project makes several significant contributions to the body of knowledge in the field of facial recognition and emotion detection. The main 4 points are advancement of machine learning techniques, integration of multimodal data, and ethical consideration of the user privacy. Overall, the project's contribution to the body of knowledge encompass technical advancements, ethical considerations, user-centered design principles, and interdisciplinary collaboration, positioning it as a valuable addition to the ongoing discourse on facial recognition and emotion detection technology. When talking about the novelty component, there are main 4 novelties. Multimodal integration. The project uniquely combines audio, text, and visual data for emotion detection, providing a more comprehensive and accurate analysis of emotional state compared to the traditional single model approaches. The second point is real-time emotion detection. Implementation of real-time emotion recognition capabilities enabling continuous monitoring and immediate response to detect emotional changes. Third point is advanced machine learning techniques. Utilize cutting-edge deep learning models including CNN and NLP techniques to enhance the precision and reliable of emotion detection. Last novelty point is contribution to research and practices. Talking about the limitations and the future enhancements, there are 4 main points: data diversity, real-time processing, privacy concerns, and contextual understanding. The use of the new skills are advanced deep learning techniques and the hybrid model integration. When moving to the existing skills, machine learning and deep learning skills, programming and software development, data science analytics, and project management and problem solving skills.